We're going to learn duality and kind of general convex problems today, and we'll actually say a few things even about non-convex problems as well. Duality is a very kind of general, very general concept. So just to remind you what we did last time, we talked about duality in LPs last time, and we had this very kind of explicit hands-on construction for the dual of a linear program. So if we had this kind of general form linear program, which we called the primal LP in the context of, the primal, in the context of the dual, we called this one the primal. And we derived something called the dual linear program. So it was the dual of this convex problem, and it also happened to be a linear program. And the way that we went about that was that we had this idea that we wanted to lower bound the primal criterion value at optimality. So if we called the optimal value of this LP f star, the primal LP having optimal value f star at the solution, we wanted to construct a lower bound to f star. And so what we did was that we actually took something that we called dual variables, u and v, and we restricted v to have non-negative components because we were essentially going to be multiplying every component of the dual variable by a constraint here to generate new constraints. And because of the less than or equal to sign, we required that the constraint we multiply by the ith component of this system of inequalities, gx less than or equal to h, had to be non-negative so it didn't flip the sign. Okay, so as long as v is non-negative in each component and u is anything, we know that this is true for all feasible points x, right? U transpose ax minus b is 0 because ax minus b is 0 when x is feasible, and v transpose gx minus h is non-negative because this guy is less than or equal to 0 in each component, and this guy is bigger than or equal to 0 in each component. Okay, and then the game was that we observed that this was true for every feasible point x. So we tried to rearrange this in order to make it look like the primal criterion, C transpose x. So we collected all terms that depend on x. That gave us this thing, minus A transpose U minus G transpose V, that quantity transpose x being bigger than or equal to minus B transpose U minus H transpose V. So again, this statement is true for all feasible points x as long as U is anything and V is non-negative in each component. And then we said if we restricted our attention to U's and V's that made this equal to C, this would give us a lower bound on the primal criterion value C transpose x, right? Because this holds for all feasible points. And to get the tightest lower bound possible, right, to make this lower bound as tight as possible, we could maximize over all points U and V that satisfied, this being equal to C, being bigger than or equal to 0, and then no sign constraints on U. And that was exactly the dual linear program. So that was the way we constructed it. The nice thing about linear programs is that you can think about it in this very kind of hands-on fashion, right? You derive a system of equations that's always true, or it's really just one inequality that's always true for all feasible points x, and you rearrange to get the criterion value. Okay, so that was how we looked at duality in linear programs initially. Yeah.
On the right side, that should be max uv, right?
Right. Yeah. Thanks. That's a typo. That should say a v. So b is just the constant here on the right-hand side. So maximize over all u and v. So that was kind of the explanation we started with. I think that was the one that is easy to remember for linear programs. The second explanation that's slightly more subtle that we went through that ends up being very, very important in the context of general problems, general convex problems or optimization problems. And that was the following. So we looked at the primal criterion value, and for the same reason that we said this was less than or equal to 0, right? For the exact same reason, the same logic, we know that for all feasible points x, C transpose x is bigger than or equal to C transpose x plus that same quantity, U transpose AX minus B plus V transpose GX minus H. Because, again, just because this thing is always less than or equal to 0 for all feasible points x, as long as V has non-negative components. Okay, so we're invoking that same kind of key property, but we're using it in a slightly different way. And we're thinking of this as a function of three variables. Okay, the primal variable is x, and the dual variable is uv. Okay, the dual has a kind of pair of blocks of variables, u and v, for the equality constraints and the inequality constraints. This thing we refer to as the Lagrangian. Okay, it's a function of x, and then the dual variables u and v. So just by virtue of the fact that we have this inequality for all feasible points x, if we were to minimize over x, we would see that minimize over all x that were feasible, we would see that f star, right, on this side gives us f star, minimizing the primal criterion over all feasible points x, is bigger than or equal to, this is just kind of explicitly writing the minimum over all feasible points, which I'm denoting the feasible set by c, of the Lagrangian, L x u v. Right, thinking about this at the moment for u and v fixed and x being the argument, right? Minimizing over all x. Okay, so this is true just from this inequality pointwise for all feasible points, x. We get this. This inequality, this is maybe where I think, I think this is extremely simple, but it's a subtle idea that's very powerful. The minimum over all points x that are feasible is bigger than or equal to the minimum over all x unconstrained, right? That's an extremely simple idea, but it's really this inequality that allows us to lift duality to general optimization problems. Right? Again, if I just make the minimization domain larger, the minimum can only get smaller. That's all we're saying here. And it turns out that this is actually, this inequality, what we're going to see later on, this inequality is actually tight at the dual solution uv. So we haven't lost anything by actually kind of getting rid of the notion of the feasible set. This inequality is, even though it seems extremely loose in general, it's actually tight at the right u and v, which we call the dual solution. Okay, but just forgetting that for the moment, just thinking of these as inequalities, this now is a function, usually a calculable function, that's the nice part, of just u and v, right? The minimum over all x. So we've minimized out x. This is just a function of u and v. We denote that usually by g u v, and we call this usually the dual function. So in other words, this is a lower bound on the primal criterion value f star for any u and any v bigger than or equal to 0, right? This is exactly what we've shown. And in the context of our linear program, right, what was the Lagrangian? It's actually this guy up here. Okay, and if we rearrange this to just make this look like a function of something transpose, of the form something transpose x, right, we get that this is just c, right, that's the first term, minus a transpose, or sorry, plus a transpose u plus g transpose v transpose x minus b transpose u minus h transpose v. Okay, that's what the Lagrangian looks like, just rearranged. And if we were to minimize this over all x, we would get two things. Minus infinity if this thing wasn't 0. And if this thing was 0, we just get minus b transpose u minus h transpose v. So that is the Lagrange dual function, right? We have an explicit form for it. And then it's the same idea as earlier, right? Maximizing this over all u and v gives us the tightest lower bound possible. We call that the dual program. And these two constructions give the same thing in this case. Okay, the beauty of the second explanation is that it's much more general, and that's what we'll kind of go with today. Okay, so here's the outline for today's lecture. We'll talk about these things just in a bit more detail, the dual function, the dual problem. We'll introduce notions of weak and strong duality. We've kind of mentioned these words already, but we'll make them formal. We'll give some examples, and then we'll kind of preview, I think, just one use of the dual. And then we'll have a lecture. We'll revisit uses of duality in just a couple lectures. Okay, so we're going to move away from linear programs. We're just going to consider the most general form of optimization problem that we can. And we're not even going to somehow require that our optimization problem is convex at this moment, but of course we're going to kind of pay special attention to the case when it is convex. So our criterion is f of x. Our constraint functions we're denoting by hi of x. These are the inequality constraints. And the equality constraint functions we're calling lj of x equals 0. Okay, so of course we know that if we were restricting our attention to convex problems, we need to have f being convex, hi being convex, and all the lj's being affine functions. But right now we're just going to kind of write these in a very generic form. Okay, these can be anything at this point. We're going to define the Lagrangian. This is kind of exactly what we did before, okay, as the criterion value plus the sum of some dual variables times the inequality constraint functions. These are the guys we call the dual variables, ui, plus the sum of some dual variables vj times the equality constraint functions, lj. Okay, and again, just as we had before, we're going to say that the dual variables that multiply the inequality constraints must be non-negative. Okay, because we're going to try to invoke a relationship between this thing and x and f of x, And so we're not going to somehow want to flip the sign of this inequality, right? We know that hi of x is less than or equal to 0. We're going to keep ui being non-negative. Yeah, question? Yeah, that's a fair question. So the question was, why do we write these explicitly as equality constraints? I'm doing it because I want to separate out kind of dual variables that are unconstrained in terms of their sign from those that are constrained. Okay, it's just notation, basically. Other questions?
We studied something in another course about Lagrange multipliers, where if you had some constraint, you would add lambda times that. I guess they're related, but that's the Lagrangian and Lagrange multipliers are two different things, right? So you multiply.
I would say they're actually the same thing, but maybe we'll kind of hold off on why they're the same for a few lectures. But let's just say that some people call these Lagrange multipliers. Okay, some people will call these dual variables, some people will call these Lagrange multipliers. It depends on the context. And the idea of kind of lifting a constraint into the criterion via Lagrange multiplier is really the same as duality. But it's a good question, yeah. So you might see these written down as Lagrange multipliers or dual variables. Other questions? Okay.
What happens in the non-convex case?
Nothing changes so far. So we're going to consider a general optimization problem. So you can think of this as non-convex for the moment. And then we'll kind of diverge at some point. So this is the very important property. So everything we're going to state today is very simple. Everything we're going to state today is, the proof is going to be maybe one or two lines, but it's kind of has very powerful implications in some sense. So, we're going to be saying things like this. Okay, the criterion value is larger or equal to the Lagrangian for all u that are non-negative and all v. Okay, as long as x is feasible. Why? It's really the same idea we use for linear programs, which is that just write out what the Lagrangian is. It's the criterion plus the linear combination of dual variables and inequality constraint functions, and linear combination of dual variables and equality constraint functions. And when x is feasible, this thing is 0, right? By definition, it must satisfy each equality constraint. This thing is less than or equal to 0, again by definition. And this ui, we're saying, is bigger than or equal to 0 for all I. Okay, so this whole thing, this whole term we've added to the criterion is less than or equal to 0, right? Because this guy is 0, and this guy is just the sum of things that are non-negative times things that are non-positive. So bigger than or equal to 0 times less than or equal to 0. Add those up. The whole thing is less than or equal to 0. Okay, so therefore f of x plus all this stuff is just less than or equal to f of x. Okay, so here's a demonstration of what this looks like. So I've drawn the criterion as a solid black line here. Actually, I didn't personally draw this. This came from the Boyd and Vandenberg book. So there's this criterion here drawn as a solid black line. That's f. You can notice it's actually non-convex, just to make the point that this is not somehow restricted to convex optimization problems, this notion. And this dotted line here is the constraint function. So let's suppose we have one inequality constraint, and we're solving an optimization problem in one variable, and it's of this form. Okay, minimize over all x, where x is univariate, f of x, subject to h of x is less than or equal to 0. Okay, so we just have this very simple problem. And for when h is less than or equal to 0, we kind of restrict ourselves to being about minus 0.5 to 0.5. Okay, so this is the feasible set. Say it's this interval right here. What we're drawing is, in these dotted lines, okay, is the Lagrangian as a function of x for different values of u. So for each different value of u, I can write down this Lagrangian. Okay, and u has to be non-negative. I have no v's here because I have no equality constraints. It looks like this, right? It's just this function. Okay, there's no v's. It's just this function. And I'm going to look at different values of u greater than or equal to 0. So let's suppose we picked u equals 1 or something. Then what's being drawn in that picture is that we have the criterion here. And for every value of u, I'm applying the Lagrangian as a function of x. And you can see, I won't kind of replicate all the curves, but the point is that it lower bounds the criterion value over the feasible set. Okay? For every x, each one of these dotted lines is less than or equal to everywhere in the feasible set, this solid line. Each one of them is just one of these realizations of the Lagrangian when we plug in one value of u that's bigger than or equal to 0, and we look at it as a function of x. Okay, so this is just this property visualized. Questions?
Wait, how about outside of the feasible set? Is it always tested automatically?
It's a good question. So in this case, so if we have one constraint function, you can see, at least in this example, it is the case that it's bigger than or equal to Lagrangian, right? Well, why is that? Because outside of the feasible set, this function is positive, right? So we're adding something that's strictly positive, or at least non-negative, to the criterion. What do you think happens in general if we had more than one constraint? Suppose we had two constraint functions. So I had h of x less than or equal to 0, and I had another function, h prime of x less than or equal to 0 or something. Would I always have the property that outside the feasible set? Right. So even without the equality constraints, though, you could argue that directly that it's not necessarily the case that it's bigger or equal to the criterion value, right? Because if I have two constraints that are both non-negativity constraints, and one is not satisfied, if that gives me a positive value of the inequality constraint function, it still matters what the other value is, right? When I'm adding it to the criterion Lagrangian. So it's just not clear. We don't have this. We don't have a definitive property in general outside the feasible set. But we don't really somehow care about that. That's okay. It's a good question, though. Other questions? Okay, so the Lagrange dual function is kind of the first thing we'll define, I guess the second thing, next to the Lagrangian itself. And it's defined, again, analogous like we did to linear programs. And again, just very simple arguments to get us there. So because we have this property that, the Lagrangian, right, is always less than or equal to f of x for all feasible points x, and all u that are bigger than or equal to 0 and all v, if we just fixed some u and v with the property that u was bigger than or equal to 0 in all components and just v was generic, and we thought about minimizing this thing over all x that are feasible, then that would be less than or equal to f star, right? Again, it just comes from, say, this picture. Whatever I fixed for u and v, this function would just always be below the criterion value. So if I minimize it over the feasible set, its minimum has to be smaller than or equal to the minimum of the criterion over the feasible set, which is just f star. Okay, so this follows just from taking a minimum on both sides of this inequality here. And then we invoke this idea that if we were to get rid of the constraint set, the feasible set, in our minimization, then this can only make the minimum smaller. Okay, so this is why this inequality happens. We've already kind of talked about that for LPs, and it's the same concept here. It's nothing's kind of specific to the criterion. We're just saying that the minimum over a bigger domain, which is just everything, is less than or equal to the minimum over C. And this thing we define as GUV. Okay, and it's usually or often calculable, so that's why we kind of like to think of this as just being a function of u and v. Of course, so is this, right? Some people maybe get a bit confused and say, well, why don't we just stop here? I could just define that to be GUV, right? That's also just a function of u and v. But that's usually not a useful assertion. Okay, it's usually this that is the useful assertion that gives us something that's kind of tractable. Okay, this is because there's no constraints here, we can usually calculate this minimum either analytically or in some cases we can express things about it. As we'll see later in the course, it still makes this a useful relationship. So this is just defined as the Lagrange dual function, the minimum of the Lagrangian over all points x unconstrained. Okay, and we think about it having a domain, which is just u being bigger than or equal to 0 and v being anything. So we can't evaluate this function at anything. We can only evaluate at u that are bigger than or equal to 0 and v that are generic. Okay, so that we think of that as being the domain of the Lagrange dual function, or at least those as being part of the domain. Okay, we don't think of this as being defined outside of that. And okay, so here was this example carried over from the last slide. So what we did is for each fixed u and v, okay, and in this case it was just u, right? We didn't have any v's because there's no equality constraints. We just thought about minimizing this function, one of these dotted functions, over all x, not just in the feasible set, but over all x. And we defined the Lagrange dual function as the smallest value it possibly attained. Okay, and that's what we're showing here. And we're comparing that, this is the function. So in the Boyd-Vandenberg textbook, they called the dual variable lambda, it's just RU. This is what that looks like as a function of the dual variable, the single dual variable. And this is the primal criterion value. Okay, so we can see that indeed we have this property that the dual function lies below the optimal primal criterion value for all, in this case, u that are bigger than or equal to 0, right? Because we had an inequality constraint, its domain was just the positive real line. Okay, we actually noticed something kind of interesting here, which is kind of foreshadowing something to come up, which is that these aren't the same. So the biggest value I could make the dual function is not the smallest value I could make the primal criterion value of the feasible set. So who can guess why that's the case? Based on this example, what did I say about this example? Maybe made it a bit unusual compared to what we usually look at in this class. Non-convex, yeah. So we're going to kind of see that, generally speaking, duality provides us with kind of like a tight lower bound for convex problems, but for non-convex problems, that's not necessarily the case. Okay, it's not that it doesn't happen, it's just that we don't really know that it's always true. So let's go through a slightly more sophisticated example, a QP in standard form. So our problem is going to be 1/2 x transpose qx plus c transpose x, subject to the equality constraints ax equals b, and the inequality constraints x being bigger than or equal to 0. Okay, and q is going to be positive definite here. We'll say it's lowest eigenvalue is actually strictly positive. That makes this problem strictly convex, right? So the Lagrangian just kind of follows from our usual recipe, which is we take the criterion value, 1/2 x transpose qx plus c transpose x. We add, let's say, v transpose times the equality constraints, right? Really, we could write it like this if we wanted to match our notation from the previous slide, but it's the same thing. Right, we're going to have the sum of ui times the inequality constraint functions, and those are just actually minus xi. If we wanted to write it as something being less than or equal to 0, it's just minus xi less than or equal to 0, plus vj times the equality constraints functions, right? Something being equal to 0, and that's just each component of ax minus b has to be equal to 0. So that's how we could write it if we wanted to somehow use the notation from the previous slide, but we can also just say this is a, more succinctly, it's just this. Okay? So that's Lagrangian. And let's think about forming the dual function. Okay, it's going to be a function of u and v. Right? We're going to get rid of x by minimizing out over x. And we're not going to have to think about this constraint set anymore. We're going to completely kind of forget about it for the moment. Just minimize this function over all x. Okay, so GUV, right, is the minimum over all x of the Lagrangian. And in order to think about what that is, it's helpful to collect terms so that we have a single quadratic in x. Think about u and v as fixed. Okay, so that was the only quadratic term we had. And how about for the linear term? We can write it as c minus q plus a transpose v transpose x. Right? And then there's just this term minus b transpose v. Or v transpose, whatever. Minus b transpose, that's fine. Okay, so what's the minimum of this over all x? How would you figure that out? I think I heard the suggestion. Just take the gradient, set it equal to 0, right? Which we can do. An aside, I always remember this fact for quadratics. Like I always remember the gradient of the least squares loss function because I had to take that thing a million times. I just remember what the rule is for quadratics, for minimums. So for a one-dimensional quadratic, its minimizer, let's call it x star, is just minus b over 2a. Okay? That just comes from, again, differentiating and setting equal to 0 and solving. For a quadratic of this form, let's say, 1/2 x transpose qx plus b transpose x, its minimizer is, well, it's actually just this equation. It's just written in matrix form. Okay, the minimizer is just, well, I have to divide by 2a, but a here is actually a matrix, so it's just minus q inverse b. So that's how I remember what it looks like for quadratics. So let's just apply that here. This whole thing is just this, what I called b here, right? So the minimizer is, of the Lagrangian, is just minus q inverse times this thing, c minus u plus a transpose v. And so the minimum of the Lagrangian is what happens when I plug in that minimizer. Right, it's just L of x star uv, which is, well, here I get minus 1/2 times this transpose q transpose this times this, and I'll have q inverse times q inverse, so one of those will cancel, and it'll just end up being minus 1/2 times c minus u plus a transpose v transpose q inverse c minus u plus a transpose v. And here I'll have this transpose minus q inverse c minus u plus a transpose v. Actually, here I shouldn't have a negative, right? Because I had two negatives. I had one for each term involving x. Okay, and yeah, and here I should have minus c minus u plus a transpose v transpose, that's this thing, my solution, just q inverse minus c times c minus u plus a transpose v. Sorry, I put it off the page. And then I have that leftover piece, that little, just minus b transpose v sitting around. And so you can see I have a half of a quantity minus the same thing. So it ends up just being minus 1/2 times this quadratic, c minus u plus a transpose v transpose q inverse c minus u plus a transpose v minus b transpose v. So that is explicitly the Lagrange dual function. Okay, it's a function of u and v, and we think about it as having a domain which is restricts u to be non-negative, right? And v can be anything. So for if you give me any u that's non-negative in each component and any v, this thing actually lower bounds the optimal value of this quadratic program. Okay, it's a highly non-trivial statement. I mean, this in a sense is almost trivial because we have it written in a very kind of general form, right? All these inequalities are due to like one-line justifications. But think about the implications for a problem like this. Highly non-trivial. So that's a general form quadratic program. It's not at all obvious that this thing actually lower bounds the optimal value, right? It's completely not obvious. But the justification from it is just that, well, this is the property of the Lagrange dual function, which we proved is true in like just a couple of lines. Right? This thing lower bounds the optimal value of this standard form QP as long as a u is positive in each component, or non-negative. Okay. I think it's maybe worth actually going over this. I was thinking about skipping this, but maybe it's worth going over it so you can see what happens when there are more kind of constraints in the domain of the Lagrange dual function. So let's do the same thing, okay? But let's think about a QP where the quadratic, the matrix Q is positive semi-definite, not necessarily positive definite. So it could have a null space, right? There could be some vectors x for which qx is equal to 0, but x is not 0 itself. So how does that change the Lagrange dual function? Let's work that out. So same thing as before. Let's write down the Lagrangian, and we'll skip right to the form we had last time, which was kind of combining all these things into just one linear term on x. Okay, now we want to minimize this over all x. Well, what goes wrong is that Q inverse doesn't exist anymore necessarily, right? Q need not have an inverse. It's just positive semi-definite. So what happens if you try to minimize a quadratic, okay, that has no, that doesn't necessarily have an inverse? Well, still, this is just still a convex function. We can still take its derivative and set it equal to gradient, set it equal to 0, and we get just qx equals minus c minus u plus a transpose v. We still are seeking a point x that makes this true, right? If we could find an x that makes this true, then we could plug that in and find the minimum of the Lagrangian. But the difficulty here, and again, the linear system, is that this matrix need not have an inverse anymore. So there's kind of two cases that we have to think about. So the first case is when this thing, c minus u plus a transpose v, c minus u plus a transpose v, it's in the column space of Q. Okay, that means that there is an x that makes this true. This is not, this linear system is satisfiable, right? There is a solution. Okay, in that case, in that case, okay, we can actually write x as a solution, let's say x star, as the generalized inverse of Q times minus c minus u plus a transpose v. Okay, this thing, Q pseudo-inverse, it's sometimes called the generalized inverse of the pseudo-inverse. It's usually defined in terms of the singular value decomposition. So if you write, or I guess Q here is symmetric, so we can use just its eigendecomposition. So suppose we were to write Q as u du transpose, right? If Q is positive semi-definite but not positive definite, then D has some possibly 0 entries, right? Diagonal entries. So we can think about it like this: D1 through dr, and then 0, 0, u transpose. And the way that we define Q pseudo-inverse is usually via this eigendecomposition, or an SVD for a rectangular matrix. And we define it by, so what would Q inverse be? Let me, before I tell you what Q pseudo-inverse is, what would Q inverse be if I just gave you an eigendecomposition and actually all of these diagonal elements were positive? How would I write Q inverse in terms of this eigendecomposition? It would just be u d inverse u transpose, right? You can check that's the case by just multiplying the matrix by Q. Remember, U has orthogonal columns. So in terms of the eigendecomposition, Q inverse is just u d inverse u transpose, right? Multiply those two together, you get the identity. For the pseudo-inverse, we can't do that because we can't actually invert the diagonal elements, right? We can't take d inverse, which would involve inverting the diagonal elements, because sometimes they're 0. So the way that the pseudo-inverse is defined, again, sometimes it's called the generalized inverse, is by inverting the diagonal elements that are positive and leaving the rest that are 0 as they are. So this is the definition of the pseudo-inverse. And you might hear this sometimes called the Moore-Penrose pseudo-inverse, because there are actually different types of pseudo-inverses. But this is the standard one. It's one that everyone kind of refers to as a pseudo-inverse. Okay, so again, if this might be new to some people, but I presume that people have seen something like this before. We can write a solution to this linear system, provided that this is in the column space of this matrix Q, by, instead of the inverse, the pseudo-inverse. Okay, so this is a solution to this linear system. And in that case, we plug in this back into the Lagrangian, and we get the dual function, which is the same as we had before, but I have Q pseudo-inverse here instead of Q inverse. Okay, Q plus. Sometimes you'll see that written also as Q dagger in LaTeX, like instead of a plus, the dagger symbol. Okay, but there's one other case we didn't consider, and that's the case when this has some component that's actually not in the column space. Okay, it has some component that's in the space orthogonal to the column space, which is the null space. Because this matrix is symmetric, its column space and its null space are orthogonal complements. So I can actually rewrite this as C minus U plus A transpose V is orthogonal to the null space, because the column space and the null space are orthogonal complements for a symmetric matrix. And the second case is that it's not orthogonal to the null space, which means that there's some kind of piece of it that actually lies in the null space. So not orthogonal to the null space. Okay, which means I can write this. Let's say I write this thing as, let's call it Z1 plus Z2, where this thing is in the column space of Q, that thing's in the null space of Q. Right? Z1 is in the column space of Q. Z2 is in the null space of Q. And Z2 is not equal to 0. Okay, so this is what I mean by being not orthogonal to the null space. So what happens in that case? Well, in that case, this has no solution. And if we go back to the Lagrangian, we can ask what happens if we were trying to minimize over all x in such a case, right? When U and V are arranged so that it's not orthogonal to the null space. You can actually see that we can make this we can make this as small as we want, all the way to minus infinity, right? Because if I just take x to be some scalar multiple of, say, Z2, or of minus C2, then this term is 0. Because by definition of the null space, Q times Z2 is going to give me 0. But this term is not 0. That's the key. And if I take x to be, some scalar multiple of minus Z2, then I can make this as small as I want. I can drive this term all the way to minus infinity. So in that case, right, the Lagrangian, if I want to minimize it over all x, the answer is just minus infinity. So this is an example where we get something that's called an implicit domain constraint in the dual function. So the Lagrange dual function now, right, it's basically defined according to two cases, right? It's either what we had before, which was this quadratic, times a half, right? In case 1, when U and V satisfy, this is actually like a series of equality constraints, right? I'm saying they have to be orthogonal to a linear subspace. And otherwise, it's minus infinity in case 2. And so what we think about is actually, it's like adding a domain constraint. We're saying we're only considering U and V such that this is true. C minus U plus A transpose V is orthogonal to the null space. It's actually quite similar in a sense to what we saw for LPs, just a little more complicated, right? The LPs, we had something similar. It just ends up being a much simpler domain constraint. Okay, questions about that? Okay, so now we have, in this case, let's just maybe back up and think what we got. When we had a QP, the Lagrange dual function was actually a quadratic, right? So maximizing the Lagrange dual is still a QP. Kind of interesting that the duals of QPs are also QPs. This QP, the Lagrange dual function is a quadratic, but with a domain constraint that looks like this must lie in a linear subspace. But we can write this actually as equality constraints on U and V. Okay, this being orthogonal to the null space of Q means that if I take the projection matrix onto the null space of Q, call that P, and I multiply this by P, I should get 0. So I can think of that as a bunch of equality constraints on U and V. So again, it's a quadratic function, and if I wanted to maximize over all u and v, I'd get a QP, right, just with some extra equality constraints that came from this. Okay, so just to say that maybe to write that down so we don't forget, it's just, I'm just saying that actually case 1, which is C minus u plus A transpose V being orthogonal to the null space of Q, that's actually equivalent to a matrix P times C minus u plus A transpose V being equal to 0. I can think of that as just a bunch of equality constraints on u and v, where P is the projection matrix onto the null space of Q. Okay, another example I wanted to go through is a much simpler quadratic program. It's just a two-dimensional problem. So let's suppose that I had my criterion being a quadratic in 2 variables, and I didn't have any equality constraints. I just had inequality constraints, right? X is bigger than or equal to 0. Then in this case, right, I minimized over all x some quadratic function subject to x being bigger than or equal to 0, and this was, let's say this is a quadratic function, x transpose qx plus b transpose x, say. The dual function, right, which is just going to be a function of one variable, one block of variables, so it's just a function of u. U is two-dimensional because I have 2 constraints here, right? Let's suppose x was x1, x2. Then I have 2 dual variables, u1, u2, and it's actually itself a quadratic, right? We saw that from the previous example. Minimizing this out over all x gives me a quadratic in u. So that's what I'm showing you here. I'm showing you, in this case, this is just a graphical depiction of that particular quadratic I chose, quadratic surface over, the positive or non-negative orthant, x1, x2 both being bigger or equal to 0. And I'm also plotting through the dual function in this case, right? The dual, as we can see from all these examples, and you can tell from working this out, is going to be a concave quadratic, right? Because I have something like minus, the dual variables transpose a positive semi-definite matrix or positive definite matrix, transpose a bunch of stuff. So it's a concave quadratic. And here's what it looks like as a function of its variables. So in this example, again, I only had inequality constraints on x, so I had 2 dual variables, and I can actually kind of use these axes for 2 different purposes. This is either x1 when I'm plotting this function, or it's going to be u1 when I'm plotting this function. So I'm plotting the dual surface and the primal surface. And we can see 2 things that are kind of interesting. The first is that it looks like the biggest value that the dual attains, which I draw in this dotted line, is the same thing as the smallest value that the primal attains. So it seems like this construction is going to be tight. If I try to maximize this, I would get f star back, at least in this example. We're going to see that's not a coincidence. I didn't choose this example carefully. That's a very general phenomena for convex problems. The other thing that's kind of interesting that we see from this picture, which is we'll talk a lot about next time, is where the solution occurs, where the dual solution occurs. So today and yesterday, we're just talking about criterion values. We're not talking about solutions. Criterion values are going to match. Next time, we're talking about solutions. So let's just kind of preview that a bit. The dual solution occurs at 0, 0. The primal solution occurs, you can't really see from this picture one of the axes that well, but it occurs on the interior of this non-negative orthant. So x1 and x2 at the solution are both strictly positive. Is that a coincidence? That there's that relationship, that when x1 and x2 are both strictly positive, the dual solution is 0. Who thinks that's just a coincidence in this example? Well, I guess why would I put this example up and phrase it that way? So who can provide me with an explanation for why that's the case?
Because assuming wherever Q is
So in this case, it's actually it's a strictly convex quadratic. So Q has an inverse. Okay, so this is not a case in which. Yeah, I think that's a good explanation. I mean, you're kind of answering specifically what happens if we were to construct this Lagrange dual function, think about maximizing it. Those arguments are actually, that you mentioned, are pretty general. So in just a few words, this is the phenomenon called complementary slackness. So we're going to learn this next time we talk about the KKT conditions. If one of these constraints is not tight at the solution, the corresponding dual variable has to be 0. It's a general kind of phenomenon we're going to prove has to happen. So you can see both constraints are actually not tight at the solution. X is strictly bigger than 0 in both coordinates. That forces both dual variables to be 0 at the solution. Why don't we take a bit of an early break by our standards. Let's take a break, and then we'll come back and do the Lagrange dual problem, which we've kind of just been implicitly referring to all along when I've talked about constructing these dual functions here, right? And the Lagrange dual problem is just what we get by maximizing that dual function with the constraint that u must be non-negative, right? Because we only really define that function, GUV, for u being bigger than or equal to 0. Okay? There's an extremely important property called weak duality, and that property says that whatever we happen to find here in this maximization problem, right, in the dual problem, call that G star, that's less than or equal to F star, the optimal value in our original primal problem up there. And that was true by construction, because we constructed this dual function GUV in such a way that it was a lower bound on F star for all u and v, where u is non-negative. So if we maximize it and get G star, that's still going to be smaller than or equal to F star. Okay, this is true just by construction. Writing the dual in such a form, right, in this way, it makes it look very simple, right? We only have one inequality constraint on u. If we could find this function g, it seems like we have this like really simple problem, and maybe it's a bit deceiving. The dual is not always kind of simple in the sense that it doesn't always really have this constraint. It has can have effectively many more constraints. And to give you an example of that, well, you actually already saw an example of that with LPs. Here's the QP example. Okay, so that's the Lagrange dual function we constructed. So if we continue on with the QP dual, it's to maximize over all u and v, right, this function. But this function is negative infinity unless we have, an equality constraint holding. So actually, we have an equality constraint in the dual. We can write it like this, right? C minus u plus A transpose V transpose Q pseudo inverse C minus u plus A transpose V, subject to, well, actually two constraints. We must have this matrix P that I introduced. I introduced that matrix, remember here. I said that that matrix times this being equal to 0 is equivalent to this being orthogonal to the null space. It's the projection onto the null space of Q. So we actually have more constraints than what we kind of have transparently. So we have equality constraints and we have inequality constraints. Okay, and there we'll see other cases, many of the cases where we just kind of get a bunch of constraints in the dual. It's not always, as simple as it may look here transparently. It comes from the fact that by minimizing Lagrangian, we kind of arrive at a bunch of implicit domain constraints for the dual function, which we can write as constraints in the dual problem. Okay, so this relationship weak duality, it always holds even if the primal problem is non-convex. Kind of amazing in the sense that you can have any incredibly non-convex, very complicated optimization problem. You form the dual, it always lower bounds the primal criterion value. Sometimes if the criterion value is itself of interest, that may be good enough. Maybe you just want to know something like, you know, if this is some kind of cost, or if this is a maximization problem and it's like some utility and you want to know something about the optimal cost or the optimal utility, then maybe actually getting a lower bound when this is a minimization problem or an upper bound when this is a maximization problem, maybe that's actually of interest itself. And you can do that by forming the dual. Okay, and I guess just to say that, to reiterate something I just said, if this was a maximization problem, we could form a dual that was a minimization problem, just by kind of repeating the very similar steps we'd already done. So another key property, which I think is surprising when people see this for the first time, is that the dual problem is always a convex optimization problem. Okay, so as written, because we wrote the primal as a min and the dual as a max, the dual is always a concave maximization problem, which we know is equivalent to a convex minimization problem, right? Just by taking the negative of g as the criterion and minimizing instead of maximizing. So that's why we call it convex optimization. So this is always true. It's always true. It's even true when the primal is non-convex itself. Okay. Again, people I think are surprised when they see this for the first time, but in a sense that means that if we could get here, we could always solve it, right? Because convex problems, if you're lucky enough that CVX would cover it, you can solve it. If you're unlucky that CVX can't cover it, then you can compute subgradients, use a subgradient method, right? Or just that's probably the most generic thing that we know so far. Okay, but it's a convex problem, so something should work. So why is that the case? Well, we're going to prove that g is a concave function. And once we know that, it's a concave function, right, with non-negativity constraints. That's going to be a concave maximization problem. And that proof is very, very simple. So g is defined just by the minimum over all x unconstrained of the Lagrangian, right? F of x plus the sum of ui hi plus the sum of vj lj. And let's just rewrite that by putting a minus sign inside the minimization, changing the minimization to a maximization, and then putting a minus sign on the outside. So it's just helpful for us to look at it that way. Forget this outer minus sign. Okay? We're maximizing over all x some functions. And those functions, we want to think about them as functions of u and v. Okay, the variable here is uv. What type of functions are those for a fixed x in u and v? What type of functions are those? Yeah, they're just affine functions, right? Just ui times some constant, if I think of x as a constant, and lj times some constant plus a constant. So those are affine functions in u and v. Okay, and what happens if I maximize over a bunch of affine functions? Well, I get a convex function because affine functions are convex. We know that maximizing pointwise, right, for each u and v, a bunch of convex functions still gives me a convex function of u and v. So this thing is convex in u and v. Just comes from one of our rules at the very start of the class. This thing is therefore concave in u and v because I had a minus sign out in front the whole time. So that's it. G is concave in u and v. That's a convex constraint, right? U being equal to 0. So the dual problem is always a concave maximization problem. So why isn't this somehow, why is this universal fact not that useful? I claim that it's very interesting in principle and it can be useful, but it's not always useful. Why is it the case that somehow knowing that this is a convex problem, so we should be able to solve it in principle, knowing that this relationship holds, why don't we always somehow use that for non-convex primals? If you had a really hard non-convex primal problem, why wouldn't you always just form the dual and then maximize and then look at the lower bound? What's
lower bound could be that gap could be arbitrarily large.
Okay, the gap could be big, yeah. It's true. I mean, but it still could give you a lower bound, right? So what's the bottleneck really? Yeah, right. So computing there's actually computing this. So when this problem is non-convex, right? This still involves a minimization over the Lagrangian, right? It's unconstrained, so it tends to be tractable for many problems, especially convex problems. But for non-convex problems, that itself could be very hard. Right? The moment that you write down the Lagrangian, you could be out of luck if the roles of the x variables are non-convex. They play non-convex roles. So this is an interesting and important formalism. It is sometimes useful for non-convex problems. So there are some nice examples in the Boyd and Vandenberg problem where you can actually form duals for non-convex problems, and some of them are even tight in the sense that they actually give you kind of the right lower bound. But in general, it can be very difficult for non-convex problems to form, just to form the dual. So in other words, we would never kind of get here. We would never be able to write this explicitly and then try to maximize it. It could just be very hard to get there. So I chose an example where the dual actually was computable, even though the primal problem was non-convex. Just to show you the implications of this fact. And it's probably not worth going through the details carefully, but I wanted to convey to you that, again, the proof of this fact that the dual function is concave is very simple. But when you actually apply it in certain problems, it can have very non-obvious implications, just like we had already with these facts about duality. So here's this example I chose. It's a non-convex quartic function. So it's one-dimensional, x to the fourth minus 50x squared plus 100x. And let's suppose we want to minimize that subject to the constraint that x is larger or equal to minus 4.5. So here's what it looks like. This is the primal criterion. The primal constraint is that x is bigger or equal to minus 4.5. So the feasible set is basically here to here. And the solution occurs right at the boundary in this case. And this is the primal criterion value in red. Okay, it's not the global minimum. The global minimum occurs actually outside the feasible set, a little bit to the left of minus 4.5. But this is the optimal value of this non-convex univariate problem. And I formed the dual function, and I'll show you in a second how I did that. And I computed it over all u that are larger or equal to 0 numerically, right? Because I'm going to introduce a dual variable, and I only have one of them because I only have one constraint. And it's an inequality constraint, so my dual variable is going to have a non-negativity constraint. And this is what it looks like, okay? And you can see there's a gap. But what do we notice? This is actually concave. That's what we notice. Even though it's non-convex primal, the dual function is concave. And not to digress too much, but it looks very close to piecewise linear. And that's also a somewhat general phenomenon for non-convex primals. The dual function is concave, and it looks close to piecewise linear. So how did I get at this dual function? Well, you can actually derive it explicitly because we know that there are closed form expressions for the roots of a cubic function. So I wanted to minimize this over the feasible set. I could write down the Lagrangian, and I could try to minimize the Lagrangian, which had me looking at the roots of a cubic because I took the derivative and set it equal to 0. Okay, and I had to compare the roots of the cubic to see which one actually gave me the smallest value of this original function. So how much detail did I give on the slide? I guess I didn't give that much detail. So what I did was I formed the Lagrangian, right? X to the fourth minus 50x squared plus 100x minus u times x minus 4.5 u. Right? And thinking about u as being bigger than or equal to 0. And then I wanted to minimize this. So to do that, I took the derivative with respect to x, right, which gives me 4x cubed minus 100x plus 100 minus u. Set it equal to 0. Solved for all the roots, all the solutions, the roots of this cubic, right? This is a cubic in x, which we can do because there are closed form expressions for the roots of a cubic, one-dimensional. And then I had to compare, right, because this has multiple roots. I had to compare compare them in terms of their original Lagrangian value to get the actual minimum, right? But that defined for me eventually, I could explicitly write out all of the roots, compare them all. That defined for me the dual function. Okay, and if you want to follow along, you can see if you end up at this. I'm pretty sure I didn't make any mistakes, but I could have made a mistake. And this is what I got. So here's the dual function. G of u is the minimum over all kind of 3 possible roots of the following: fi to the 4th of u minus 50 fi squared of u plus 100 fi of u, where what are these fi functions? Well, they are quite complicated functions of u. Okay, they involve fractional exponents of quadratic functions of u. This one actually happens to have a negative fractional exponent as well. So this is what it is. And okay, then these constants here actually, these constants involve imaginary numbers. So this a2 is minus 1 plus, this is the square root of minus 1. This I is not supposed to be confused with that I. Maybe it's a different notation. But this actually, these are complex numbers. Okay, but this function comes out to being real value in the end. Okay, so why did I go through all this pain? I didn't, well, I guess I did this half for fun, but the other half of the reason was that I wanted to convey to you that this fact is actually quite startling in this instance. This is a concave function of u. Okay, try proving that from first principles. Imagine if I gave that to you as a midterm question or something. Prove this is a concave function of u. Our rules, I don't think, are going to be very useful here. Our rules for kind of operations that preserve convexity. But it is. It has to be, because it's a dual function, and all dual functions are concave. So a somewhat interesting implication. Something more that goes on is that for non-convex problems, we often get this near piecewise linear behavior. And I'm happy to discuss that more, but maybe if people are curious, they can come to my office hours. Okay, so let's kind of move towards the punchline, which is strong duality. So, and when does it occur? So we always have this relationship, f star being bigger than or equal to g star. That's true no matter whether our problem is convex or not. On the other hand, in many problems so far, we've actually observed that we have this equality, right? F star is equal to g star, so the primal and dual optimal values are the same. There's no gap between them. That's called strong duality. When does that occur? Well, it actually occurs very, very generally in convex optimization problems. And it occurs in almost every convex optimization problem. We just require something that's called Slater's condition. So if the primal problem is convex, okay, which we know means that F, the criterion, H, these H's, the inequality constraints must all be convex, and these equality constraints must be affine. And in addition to that, in addition to convexity, there has to be at least one strictly feasible point. So this point is in the relative interior of the feasible set. There has to just be a point inside the relative interior. The solution can lie anywhere, can lie on the boundary. There has to just exist a point x that makes all the inequality constraints strictly less than 0 and makes all the equality constraints equal to 0. Okay, feasible would mean that this is less than or equal to 0 for all h. Strictly feasible means that we just have strict inequality. As long as that's true, we have strong duality. Okay, this is usually a very, very weak condition. It's very unusual that you have convex problems for which Slater's condition doesn't hold. It means that the constraint set is somehow very strange. Okay, I think this is actually at least partially proved in Boyd and Vandenberg. We're not going to prove this, but proving that this implies strong duality, I think, given what we've seen so far in the class, that would not be, like, you could understand that proof. I think most of that is in Boyd and Vandenberg. Okay, and a very important refinement of Slater's condition, which I think we'll just call Slater's condition this kind of refinement as well, we won't distinguish between the two, is that you only actually need strict inequalities over functions that aren't affine. So if some of these were actually affine, I only need to find a point x that makes all the non-affine inequalities strict. I could actually still have these being less than or equal to 0 at such an x that I'm trying to use to certify Slater's condition, and that would be fine. That would be completely sufficient. So let's think about what this means for linear programs. Kind of back to where we started with duality. So what does Slater's condition mean for linear programs? Well, it says that we only need strict inequalities to hold over functions that aren't affine. But for linear programs, all inequality constraints are affine. So Slater's condition for LPs right, it just says that you get strong duality when the LP is feasible. Because we don't need somehow strictness anywhere, because all the constraints are just affine constraints. So as long as the LP is feasible, we get strong duality. So let's ask ourselves what happens for linear programs. If the primal is feasible, for the LP, then Slater's condition tells us that we get strong duality, which means that F star is equal to G star. Okay. Let's now go to the dual and pretend like that was the primal. Pretend like I actually gave you this linear program and I asked you to derive its dual. That's perfectly fair. I just gave you that dual to begin with. I never even showed you that. What do you think I would end up with if the world was fair? What would I end up with? The primal, right? I would just get back this program. It seems like it has to be true. You can actually check that. Take this example at the very start of the lecture. Derive the dual of this guy. We'll see you actually get this back. Okay, so the dual of the dual is the primal for linear programs. And let's think about applying Slater's condition to the dual then. Slater's condition says that if I have the dual being feasible, so I never gave you this, I just gave you this to begin with, and I looked at this linear program, then G star should be equal to the optimum value of the dual linear program, right? That's what strong duality means in the dual. G star equals the optimum value of the dual. But the dual of the dual is the primal, so we get back this conclusion. So if the dual is feasible, we get, again, that G star is equal to F star. If they're both infeasible, that's the only case we haven't considered yet, then they're not equal. In fact, what are they when they're both infeasible? This guy, if we write this as a min, say, and this is a max, then this guy is going to be equal to infinity, and this guy is equal to negative infinity. So the duality gap is as large as possible, right? So for linear programs, we pretty much always get strong duality because it holds if either the primal or the dual is feasible. We only don't get strong duality when both are infeasible. In that case, it's kind of in some sense, a very trivial situation because the dual optimal value is negative infinity and the primal optimal value is infinity. So you might ask yourself when you would encounter such linear programs in the first place. Okay. And you'll see one soon if you haven't looked at the homework yet. Hint, hint. So another thing that we're covering on the homework, so I didn't want to somehow spend too much in class on it, is the SVM dual. So yeah, I mean, this going through this, deriving the dual for the SVM is something you'll do on the homework. And kind of per what we've seen so far, the SVM being a quadratic program, we're going to get a QP in the dual as well. Okay, so I won't kind of walk you through that because that's part of the homework. But you form the Lagrangian as we've done already. Here I've introduced variables called psi. No, psi was a primal variable. V and U for these two constraints, right? So I can write that as negative psi I less than or equal to 0, and I can bring this all to one side and write that as something less than or equal to 0. And these correspond to these constraints, and these correspond to those constraints. And then we minimize out this quadratic. So one maybe thing just to be aware of, in case you're finding this tricky on the homework, is that it's a quadratic, but you can also minimize out over each block of variable. Right? So it's a nice quadratic where kind of the roles of beta and of beta of naught and of psi separate. So think about minimizing this out first over beta. Take all the terms that involve beta, put them somewhere. They won't actually involve psi or beta naught. Minimize that over beta. That'll give you some piece of the dual function. Then collect the terms that depend on psi. Minimize that over psi. And we can just kind of eyeball it. The role of psi is actually linear, right? There are no appearances anywhere else than these guys of psi. They're all linear. So minimizing a linear function is going to give you a bunch of constraints, right? Because it's going to be negative infinity if you didn't have a bunch of constraints. And the last thing is beta naught. So the role of beta naught is also linear. So minimizing out over that part is going to give you more equality constraints. So we should get some bona fide part of the dual function for minimizing over beta, and then the rest we should just get constraints. So maybe that was just a bit of a hint for the homework. And that's the answer, which is, that's what we should be arriving at, this problem right here. This is the SVM dual. Okay. Why do we visit this in this lecture? Well, we can check that Slater's condition is satisfied, right? If we go back to this problem, this is convex. It clearly is feasible, right? I can just take all the variables to be 0, or I can take, for example, all the beta variables to be 0 and the size to be 1, and that's clearly satisfies all the constraints. So it's feasible, and so we get strong duality. So that means that if we were to minimize the SVM problem or maximize the SVM dual, we'd arrive at the same value. And something more is true with SVMs, which is that we can actually express the primal solution beta in terms of the dual solution W. So again, this goes beyond what we talked about in today's lecture. In the last lecture, we just talked about criterion values being equal. This is actually somehow the solutions you can express one in terms of the other. This is very, very useful, right? It's a very, very useful kind of extension of duality. And we'll talk about this next time when we talk about the KKT conditions. I'll finish up with just one use of duality, and then a week from now we'll talk about more uses of duality. And that is the duality gap. Again, a very simple thing, but it can be very useful, say, when you're looking at iterative algorithms for optimizing the primal and the dual. So if you have any primal feasible x and any dual feasible uv, then if you evaluate the primal criterion and you evaluate the dual criterion and you look at the difference, that's called the duality gap between this primal point x and this dual point uv. Okay, again, these must be feasible. This must be feasible for the primal. This must be feasible for the dual. And why is that useful? It's because the duality gap always upper bounds, say, the suboptimality gap that you're looking at the primal iterate x. Okay, f of x minus f star is always less than or equal to f of x minus guv. Why? It's just because this guy is a lower bound on f star. So when you take the negatives, the inequality flips. That's it. So that's very useful because suppose you're running an iterative algorithm on the primal and the dual, okay, and you want to ask how far am I away from the optimal criterion value. Well, take the current value of the primal iterates and the current value of the dual iterates and subtract the difference in the primal and dual criterions. That tells you that you're no farther than that. Like if that's 0.001, then you're at most 0.001 suboptimal in the primal, right? F of x minus f star is at most 0.001. Also, it's true that you're at most 0.001 suboptimal in the dual. Okay, the same argument to show you that g star minus g is also bounded by the duality gap. Okay, so that's the algorithmic viewpoint, which is, it can be very useful as a stopping criterion. In some sense, it's the only stopping criterion that we've learned so far that is delivers you with a guarantee an epsilon suboptimal solution, right? This is a practical strategy that guarantees you that this is true in practice. It's also a very important thing to recognize also when we talk about the KKT conditions, in that if I ever have an x in uv for which this is 0, that implies that actually x is primal optimal and uv are dual optimal. Okay, if I'm lucky enough to find something for which the duality gap is 0, I have the solutions, both primal and dual solutions. Okay, and we'll talk about that next time.